Let's take a look at exercise 6.2.19, and let's use Gaussian elimination to find the complete solution to this system of equations, or we'll show that no solutions exist. So let's take a look at this one, and notice that we have 3 variables and only 2 equations. Whenever that happens, you cannot get a unique solution. If you have less equations than variables, your only possibility is that you are going to either get a dependent system or an inconsistent system. So in column 1, we're going to put the coefficients of x. In column 2, we're going to put the coefficients of y. Column 3, we're going to put the coefficients of z. And we're going to put a vertical dividing line where the equal sign goes. And on the opposite side of the equals from the variable terms, we have our constants. Alright, so whenever you have less equations than variables, either you're going to get a dependent or inconsistent system. Only option. Alright, so my first step is going to be to get a 0 in column 1. So notice my process is the same. I start from the leftmost column, move to the column right next to the dividing vertical line, and I get zeros on the non-diagonal elements of that column. So I'm going to get a new row 2 by multiplying -6 times row 1 and adding that to row 2. And I'm going to have to so my anchor row is row 1. So I work in column 1 to get the zeros. The anchor row is column 1. It's row 1, I'm sorry, if I'm getting zeros in column 1. So -6 times 1 plus 6 is 0. -6 times 1 plus -1 is -7. -6 times -7 is 42, plus -12 is 30. -6 times 7 is -42, minus 5 is -47. Alright, so now I've got column 1 just as I want it. A 1 in the diagonal element of that column, and everything else is a 0. Now I want to go to column 2, and I want to get a 0 on the non-diagonal element of column 2. And notice that's only one element. Since there are only 2 rows, there's only one element I want to become a 0 in column 2. And that's in row 1. So I'm going to do -7 times, let me put my anchor row first. I'm not going to do anything to row 2. That's my anchor row. And I'm going to add to that 7 times row 1. And that's how I'm going to change row 1. So R2 plus 7 times row 1 gives me a 7 in this first position. And notice, let's copy our anchor row. We get into zeros in column 2, so we don't make any changes to row 2. Seven times 1 plus negative 7 gives me 0. 7 times negative 7 is negative 49, plus 30 is negative 19. Okay, now I'm doing 7 times 7, which is 49, plus negative 47, which leaves me a 2. And to get my 1s, so now I'm essentially done. There are no more diagonal elements. If I only have 2 rows, I'm only going to have diagonal elements in columns 1 and 2. So I'm now going to get my 1s. I'm going to multiply 1/7 times row 1. And I'm going to multiply negative 1/7 times row 2. So I get 1, 0, negative 19 over 7, 2 over 7 as my new row 1. 0, 1, negative 30 over 7, 47 over 7 as my new row 2, and this is actually my reduced echelon form. Alright, so the problem told me to find the complete solution to the system of equations. So notice that this row 1 is telling me that x minus 19 over 7z is equal to 2/7. Row 2 is telling me that y minus 30 over 7 z is equal to 47 over 7. So this essentially tells me that x is 2/7 plus 19 over 7z, and y is 47 over 7 plus 30 over 7z. And so one of the things that has been happening in section 6.2 with these types of solutions is the text has been using a parameter t. So let t be used as a parameter to replace Z. So technically you could use the Z. So you can use any letter except X and Y. And so your solution set is the set of all points where X is 2 over 7 plus 19 over 7t. Y is 47 over 7 plus 30 over 7t, and Z is equal to t. So my ordered triples that solve this equation will have this format. And that's what a problem looks like when I have less equations than variables and the system is dependent.